The session is, I can't find the title. What's your official title?
Why Control System Cybersecurity Sucks.
Why Control System Cybersecurity Sucks. Stefan Lüders.
Thank you very much. Good afternoon, Las Vegas. It's a pleasure for me being here. Thank you for the invitation. In my previous life, I was physicist. Then I moved to control system engineering. I was doing safety systems afterwards. And poking around with the safety systems, I got in the job of security officer. So now I'm heading the security team at CERN. Initially, I thought the title is Why Control System Cybersecurity Sucks. But since we are partnering the 25th year anniversary of the WWW, I renamed it to Why Control System Cybersecurity is Vague but Exciting. So what I will do in the next 50 minutes is a twofold talk. First, I will introduce a little bit of CERN, doing a small session about accelerator physics. I've been asked for that. And then I will delve into our concerns or our problems with operations in terms of control system cybersecurity. So this is far away from rocket science. It is running control systems, the problems we've seen with control systems which we cannot solve with standard IT technologies. Usually what we're doing is we're handling security issues on control systems like we deal with security issues on IT systems. And we'll do a comparison between computer center security and control system cybersecurity and pinpoint down to 3 to 4 points where I'm completely fed up because I cannot treat control systems like I wanted to treat them when they would have been computer centers. So what is CERN? CERN is the European Organization for Particle Physics. We're not European anymore. Nowadays we are international, and our main business is very, very simple. This is the area around Geneva. Geneva is on the right-hand side. You see the Geneva airport. We have some tunnels underground. The largest one is 27 kilometers in circumference. And what we do is we take protons. Protons are more or less all over the place. We take 2 protons, we collide the protons, and when we collide the protons, we can look deep back into time, something like 1/1000th of a second after the Big Bang, and resimulate the conditions which were happening at that time. And we take photos of those ones. We got some digital cameras. In detail, it's looking like this. You start with protons. You put the protons into bunches. The bunches you put into beams. So each of the beam has 1,380 bunches. You put them into some kind of moulinette. If you're coming from a big city, this more is looking like the public transport. Now public transport is the same thing. You start somewhere at the beginning. If you see it here, you can't. At LINAC 2, there's a multi-layer process where you start accelerating the particles with different types of accelerators. So the protons are accelerated here, first gear, second gear, third gear, fourth gear. And once you're in the fourth gear, you have to pass everything to something larger, which is the Large Hadron Collider. This is the 27-kilometer long accelerator, which is hosting the beams in the center of this bluish tube. So you can see the 2 beams. The beams are marked here in blue and red, but usually they don't have any color. They are separate, but the size of the beam is as big as Spain on the €1 coin. Some of you might never have seen a euro coin, that's why I put a picture here. The problem with the beams is very, very simple, and this is why we need to have lots and lots of safety systems, lots and lots of control systems. The energy of the beam is equivalent of 80 kilograms of TNT. This is equivalent to the energy of a Boeing 747 fully loaded when it's starting. But our beam has a size of 4 millimeters, or the size of Spain. If this beam is getting lost within our accelerator, we destroy the accelerator, we destroy the machine, because it's like a laser saber of Star Wars. It's cutting open our accelerator, and then the beam is more or less evaporating into the tunnel. So we need to have lots and lots of safety systems, control systems, which are monitoring that the beam is exactly staying where it's supposed to be, inside the machine, but not outside. For taking the pictures, we have digital cameras. This is one of the digital cameras which is just lowered from surface to the cavern level, which is 100 meters underground. This is another one. You can see one of my colleagues standing on the platform. So just give you an idea of the size. The length of this camera is 43 meters, diameter is 26 meters. And here's another picture. You can see where the 2 beams are supposed to go. Here the beams are led in one beam pipe because we have to establish the collisions in the center of the digital camera. So what is the interesting part? It's like Indy 500. It's boring until there are collisions. So collisions are looking like this. This is a simulation of a collision. We can produce something like 40 million collisions a second, which means that the cameras are taking 40 million pictures a second. This is one of the pictures, and this is another picture. It's like a car accident. Just take it as a car accident. You can now take everything here, and you can now lead everything back and figure out what happened at the time of the collision. So what were the conditions when the collision were happening? And this gives you more or less the simulation of what happened at the Big Bang time 13 billion years ago. As I said, we're taking something like 40 million pictures a second. We process them in our local computer center, but which is not big enough to store all the data. So the data is distributed over something like 150 computer centers worldwide. The data rates we're taking per year is something like 20 petabytes or 25 petabytes. The raw data rate in the collision is something like 1 petabyte per second, which we cannot store. So we have to be selective. We're not taking every photo, but we're taking every 1 millionth photo to store this away. So in the end, this is processed, and if you process it properly and you get good physicists, then you get the Nobel Prize, which was awarded to Peter Higgs and his colleague in 2012. So just look at this. Running accelerators, running experiments needs lots and lots of control systems. Here are the list of control systems. I won't go into the details, but we need to have control systems for electricity, for cryogenics, for data taking, and so on. So those are partially control systems being developed at CERN. Mostly they are control systems which we just brought from industry, because in the end, our business model is not different than producing cars. We're producing pictures of collisions of protons, and we sell this to physicists. So here are the control systems we're running. This is it's a control system for energy distribution. We got a control system for gas distribution, control systems for cryogenics, pumping valves, and control systems for safety. We have control systems for access control. So if you want to go in, you need to go through a certain ZAS and to get access to the accelerator. This requires an iris scan of your eye just to make sure that you are you. And we get control rooms with all the synaptics, all the panels. So you see, there are plenty of control systems at CERN. And what was pissing me off when we started investigating of control systems was that the security footprint of those control systems were non-existing. When I started doing safety systems, I was able to predict my safety system. In the safety system, you can calculate what is the uptime of my safety system, what is the availability, what is the likelihood that the safety system is failing. So I was making those calculations, but I wasn't able to finish my calculation because all the control systems I was calculating on had all an Ethernet port. And then I was asking question, what is somebody like, you are hacking into my control system? And this was 2004, no one was able to answer this question to me. So I was given the mandate to investigate deeper. So we did some more testing, and every system we tested, every commercial system we tested, was showing some flaws. And this is where I started thinking that control system cybersecurity is completely vague and exciting, or completely sucks. So why should you worry? I don't know. I've collected a couple of snapshots from the media. There are lots and lots of snapshots. Some of them are true. Some of them might not be true. I can't judge. I know at least that one is completely untrue, which is the one which is appearing more or less now. Hackers defaced an LHC site and came close to switching off the particle detector. This was far from the truth, but somebody was defacing web page. But if I look at this, I think the basic questions which we're facing is, do we have a problem? Do you think we have a problem? So why nobody is caring? What I see is there are lots and lots of talk about control system cybersecurity. I see that some big vendors are acting, but most of the control systems I'm buying are from small vendors. And every time looking at the control system, I see that the security footprint of those small control systems are completely non-existing. What I'm meaning is very, very simple. We got control systems like those two. The first one is the dosimeter reader. This dosimeter is a small monitoring device which you carry on your body when you go into the tunnels. And every month you have to check out of the box. You put the dosimeter into the box, and that's reading your monthly dose. So we did a penetration testing on this device. Actually, it wasn't really penetration testing, because after 30 seconds, the penetration testing was done. What I'm doing within my team is, we get a small red team, blue team exercise. So if somebody of my team managed to get the root password of the device, I owe him a bottle of wine. If someone managed to install Nmap on a device, I owe them the crate of wine. Why Nmap? Just to prove that you can install something completely different on the device, which you shouldn't be able to. In the first case, I lost a bottle of wine. The guy who tested the device was more or less dumping the core locally on the device, extracting the core dump via TFTP, analyzing the TFTP core dump, and he found the root password for the telnet access. This was 30 seconds. Of course, we've spoken to the vendor, and the vendor promised to fix this. The second device is even more interesting. This is a power supply, which we use. We have thousands of those power supplies for control systems. You can see on the back, there are 4 Ethernet ports. One actually is a real Ethernet port. If you connect this one, and you do denial of service attack for 70 seconds, just sending random garbage to the Ethernet port, the device is dead. Dead in terms of you cannot control it anymore. You still have the power, so you still have 12 volts, 9 volts, 3 volts, minus 3 volts, and so on. But you cannot control the power anymore. The only way how to reset the device is you pull the plug. Can you think how long it takes a student of mine to run around CERN site to kill the plug of 1,000 devices in case something like that is happening? This will take him a fortune of time. So what we've seen is that the control systems we have been tested, they fulfill use cases, controlling something, guaranteeing the safety of something. But once you look a little bit different on the devices with easy tools, and this is not something of the sophisticated stuff I've seen earlier today, this is something very, very plain, low-hanging fruits, basic stuff, the devices start to failing. Security, at least from my perspective, on the control system I've seen, is not integral part of the overall. Sometimes they do something through security, like in some protocols where the vendors, in principle, say the communication is encrypted. But if you look deeper in, you figure out that it's just a little bit of shifting of ASCII codes. So we tested control systems. We took our control systems, we did something very, very simple. We just took Nessus, and we fired Nessus at the control system. This is not rocket science. Everybody of you guys can do. But if you see the outcome, this is just shocking. Devices where you send a package saying, I'm IP version 5, and the device is starting blinking in red and yellow, we're not talking about security anymore. We're talking about robustness, resilience. This is completely insane. So we tested the devices. 17% of the devices, 53 devices have been tested in 2007. 17 devices were completely failing, which means that you send them a package like Christmas tree attack or IP version 5, whatever else, and the device is dead. The control process is still pumping, and you're still able to control something, but all the network communication has ceased. The LEDs are blinking red or yellow. Network communication is dead, which means now the process cannot talk anymore with the other processes. The intercommunication is completely ceased. So now I have to go around and reset all those devices. We're talking about PLCs, embedded devices, RTUs, and so on. 15% of the devices didn't fail completely, but they failed somehow. Devices running Telnet, and you send them a Telnet password of 4,000 characters, buffer overflow, Telnet is dead. Same with the web server. Web server, URL of 8,000 characters, web server is dead. Is this supposed to be like this? I have my doubts. What I'm looking forward is, why don't we have a certification scheme for those devices? Why can't nobody come up with a list of tools, easy tools, write them on the paper, and saying, you have to test this. You run this tool, this tool, this tool, this tool. If the outcome here is A, the device is fine. If the outcome is B, the device is flawed. Just a list of tools, something very basic. If you use Nessus or if you Metasploit or whatever else, I don't care, but a list. There are certification schemes in the world which you can buy. You can buy in, and you can certify your devices for a fortune of money. But most of the vendors I'm talking to, they don't have a fortune of money. So I would like to give them a small procedure, recipe. Run this tool, run that tool, run that tool, and if the outcome is A, B, C, D, your device is, at least for that moment, for this particular recipe, at that particular date, considered to be robust or resilient enough. And the good thing is, the vendor can do the test. But I can also do the test at home. So if he's telling me my device passed the test, I can verify whether he's telling me the truth or not. Or I can give the test to a third party, and the third party can make money, like an ISO 9000 certification, running the same tests. But unfortunately, this is not existing. There is no open public security certification yet, and I'm looking forward. There are lots and lots of people thinking en gros, big-scale test stands, which has another use case, which is also good, but I'm still looking at the basics. Defense in depth is starting with the fundamentals, and fundamentals are robust devices. And what I see is the devices I'm looking at are not robust. They're completely shocking. If you just say, hey, I'm IP version 5, the device is going into the knees, and this is not something which should happen. Then we can talk about laws. I think at least in the US you can be happy that there's one law, if I'm not mistaken. In Europe they are still negotiating for the next 20 years on the laws. I feel that there are too many guidelines. There's a cacophony of guidelines. If I print them out, I think it's a heap of 2 meters. And I just need one guideline, so please do not produce more guidelines. I'm done. And then there's an unwillingness to share incidents. This is something which is now moving. But I still, if I talk to vendors, when we communicated our vulnerabilities to some of the vendors, they say, yep, but don't tell anybody, because they fear, it's fine, because they fear that somebody else might then misuse the vulnerabilities for something. So responsible disclosure is not existing in this realm. And this is the nice thing of a computer center. Computer center, I got a computer center, 10,000 servers. I can run penetration testing up and down as long as I want to. I do not fail my systems. My systems might fail, but they're redundant, so another system will take over. And we got decades of experience and knowledge in terms of security. So what we're doing now also with the control systems at CERN, we're scanning them. We're taking the burden, we're running Nmap scans against the control systems on our live and operation systems. Sometimes some of the systems might fail, but if the systems fail, we detect that they failed, we can replace them and make the whole overall system more resilient than before. So my big question is, why do I have to bear the costs of all this? Why do I have to do due diligence instead of the vendors which are shipping insecure applications or devices? Question mark. I hope this we can keep for later for the discussion, but I'm interested in opinions. At the moment, this is something what has been said this morning, like religion and software. At the moment, all the costs are with me. So I have to do defense in depth, I have to do the vulnerability scanning, and I have to bother when the device is not robust. So I have to say to the vendor, your device is not robust, what is your new product, can I buy that? And I cannot just return and saying, not secure enough, I give it back. The next problem I'm facing is with patching. This is a screenshot of an FTP welcome screen where somebody managed to hack into 3 of our devices which were connected to our office network. It's saying that he's alone and that he's offering the 6 gigabytes of hard disk for rent. If you look deeper, you figure out this is not a computer. This is an oscilloscope. If you haven't seen an oscilloscope nowadays, if you buy one from Leroy, Tektronix, HP, and whatever, those are PCs with some dedicated hardware. Lots of knobs, but here you can't see, but if you move, you see the blue screen of depth. If you move into the corner, you have still the start button. Our engineers at that moment in time didn't know that they were running Windows XP devices. So now think of that. How many devices are running Windows XP and you don't even know about this? We got a couple of oscilloscopes. You got several dozens of oscilloscopes running Windows XP, nowadays also Windows 7. And we have a problem, because now they have to be patched. Here we didn't even know, or the engineers didn't know that they can patch the device. So the usual argument why you cannot patch it is you need to make compliance testing. If you alter your control system, which has been sold to you by your vendor, then you lose any guarantees, any certification, anything else. You have to recertify your control system. If you have a safety system, you need to keep your warranties. You need to recertify your safety system that it's still safe enough that you can run it. But this holds only for a very, very small fraction of control systems. For a scope, I don't care. This scope doesn't need to be recertified. I'm thinking of the scope as a PC with some dedicated software and some dedicated hardware boards. And then the next problem with patching is there are rare maintenance windows. You cannot just patch a control system when you're in your production cycle. You have to wait for a gap when you're in maintenance mode. Think of glue, how glue is done. Glue is done in a big cylinder. As long as the cylinder is turning, your glue is staying fluid. If the cylinder is stopping, your glue is hardening out and you can throw away the whole cylinder. Now if you think the whole thing is now driven by a small Windows PC, when do you think you can reboot the Windows PC? Do you dare? Of course you don't, because you will use your product. And the same thing is happening at CERN. We got control systems which are slow. Gas distribution, cooling and ventilation, water distribution. Those are slow systems. If you shut down now a control part, a Linux server, reboot the Linux server, reboot a Windows server, you can easily do. We get other systems which are much more critical, which are time critical. If you reboot them, you lose your process. You have to wait until you get a maintenance period. We have every 6 weeks a maintenance period where we can apply patches. And then we're faced with lots of legacy, embedded devices, which you cannot patch because there's nothing to patch anymore. Nobody provides you with the most recent upgrades. So now you have to fence around and apply your defense in depth. But those are only arguments more or less coming by the vendors. The main argument I'm facing is my control system engineers are fearing to brick a device which costs them 100,000 Swiss francs. Do you dare? Think of your newest car. You bought a new car, 50,000 bucks. And now the vendor is saying, yes, you can apply now this patch, but if the patch is failing, the responsibility and the bad luck is with you. And the same thing here. Such an oscilloscope here can easily cost you 100,000 Swiss francs or $100,000. So now my control system engineers are very reluctant to apply a patch because in most of the cases, the patches can be applied. But if it's failing, and then he has a $100,000 brick sitting in his lab, who's taking now the liability? Who's taking the cost? Is it the security team because I'm forcing him to patch? Is it him and he's not taking the responsibility? Or should I go back to the vendor and ask the vendor whether he can fix the problem? At the moment, we're really doing this exercise because we have a couple of Windows XP devices and would like to upgrade them to Windows 7. Windows XP is dead, so I have to go to Windows 7. The costs are per device are between 3,000 and 10,000 Swiss francs. Just for upgrading from Windows XP to Windows 7. It's completely insane, but it's much less expensive than buying a new device. If you look at the computer center, this is completely different. When Heartbleed came out, it took me something like 2 hours to patch all the servers facing the internet. Actually, not me, but the guys who are maintaining the computer center. 2 hours. To fix everything else, 24 hours. If I need to reinstall a cluster of 7,000 nodes, 48 hours with grace periods to tell the physicist that their calculation jobs are killed and we're rebooting the servers. I can do faster, but then we will lose efficiency because then we're killing actually analysis jobs of the physicist, and we don't want to kill the analysis jobs. So usually what you do is you announce that the cluster will go down, you stop the queue so nobody can submit new calculation jobs into the computer center, and then you wait until the calculation jobs are dropping out, which is usually between 24 and 48 hours. If you do it earlier, after 12 hours, you kill the jobs, and then you reboot. Possible. We had times where we were reinstalling 7,000 nodes quickly because of vulnerability which came out a couple of months before, and we weren't sure whether we were completely secure in the computer center. Why can we do this? Because in the computer center, we have a full configuration management. In the computer center, we have software development life cycles. We get regression testing. We get nightly builds. We have virtualization. And we have full redundancy. And we try to keep the numbers of exceptions in the computer center as low as possible. Every exception is a killer. This is at least what I learned on my job as security officer. Everything what is homogeneous, heterogeneous, what is well maintained centrally, I can easily generate. I can easily handle. But then taking all the small exceptions here and there, they are costing me my time. So what we're trying now is we're trying to run our control systems equivalent to the computer center, having software development lifecycle behind, making regression testing, making nightly builds, and trying to reinstall the service also on a regular basis just to show that we can. But it's still a long way. And I think this is getting even worse. With an Internet of Things, thinking of the fridge, think of my car, my Wii, my television, my smart meter, the smoke sensor, and everything else I got in my house, now and in the future. Everything is running with some firmware. Everything is vulnerable because by default, it is vulnerable. How do we deal with the patching? Do we want to patch? Or shall I replace my television every 6 months because there's something more secure coming out? This is another discussion. I don't have a question, I don't have an answer to this one. But I believe patching must be prompt and agile. And for control systems, the same thing must hold. Here you see some other control systems. The top picture, this is a, not complete, I think this is a CAD/CAM system. And you can see on the screen the X, so you can guess now which operating system it's running. Below, this is a big laser cutter, which is running Windows XP. If you zoom into the screen, you can see the start button of Windows XP. Both devices cost you 1 million Swiss francs or dollars. We get plenty of those devices. And those devices are all bought from external company. So those external companies would like to service their devices. For servicing their devices, they don't want to come in because coming in means they have to travel to CERN, which might take them 24 hours. Then they need to do the repairs, and then need to move off again for 24 hours. So this will cost a fortune. They are asking for remote access. So if somebody now asks me, why do your control systems need to have remote access? This is exactly the argument why. Suppliers need to have access to the devices. And then they don't have even one solution. Every supplier has its own solution. TeamViewer, NetViewer, VPN in, VNC, VNC over SSH, Citrix, whatever else. Then the systems come with default passwords and undocumented backdoors, and they don't have integrated firewalls and ACLs. Access control on those devices is just a pain. The worst thing I've seen I don't even know whether I should laugh or not, is some of the control systems require to have a license at startup. And the option given to us by the software vendor was, you need to contact to our home station somewhere in the US. So I need to establish a line of sight between my control systems, behind some barriers, talking directly to a server somewhere in the US, just for activating my control system. This doesn't feel right at all. And a computer center, yes, our computer center is open because it's serving a worldwide community, but there we get all the nitty-gritty of pieces of access control. Single sign-on, LDAP Active Directory, multi-factor authentication, certificates, Kerberos, and we're even looking at identity federation in the future. So now if you think of the air gap is a myth. I think even the firewall is a myth nowadays, and it's hard to maintain. I think we should strive to having more robustness, more resilience at each of the levels, in particular on the control system. I'm not completely sure that we have this today. I'm not even completely sure whether we have this in the next 5 years. The last thing I would like to discuss is education. If I look at the CVs of my students, I'm getting students, we're getting a big folder every year of summer students, of technical students working at CERN, something like 400 to 500 students. Those are the kids, those are our kids which our programmers can use in the future. But if I look at the CVs, I'm wondering whether security is taught in the CV. If I look at them, they got a bachelor. Good, you got a bachelor. Bachelor in computer science. So they learned about databases, operating system, programming, setting up a web server. Brilliant. This is what a computer engineer is supposed to do. But then you ask for security, and you figure out, no, security is not part of my bachelor. Security I do when I do the master. This again doesn't feel right. I think security must be more embedded in the overall. Do we need to have more professionalism on that layer? If you look at control system engineering, most of the control system engineers I see and look in their CV, they believe they have ideas about IT technologies, but this is not part of their curriculum. They don't learn computer engineering. They learn control system engineering. So they don't know actually how to set up a network, but they train themselves when they're on the job. They don't know how to do patching, so they just forget about patching. And then they're doing reinvention of standard IT. Instead, they should embrace IT technologies. So our control system nowadays, when they're designed, are using Git, Jira, all the standard IT technologies, just to make it more homogeneous. What we're trying is, we're trying to bring together the controls world and the IT world, just having the same paradigms on both sides. But this is taking lots and lots of time, because if you deal with people, changing minds of people is very, very hard. If you want to convince somebody, I just suggest to you this book, Who Moved My Cheese? It's about the reluctance of humans for change. How quick are you changing? How quickly can you move from one city to another? How quickly can you move your job? The younger, the easier. The older you're getting, the more resistant you are. I got some people, in particular physicists, who are still programming in COBOL, Pascal, or BASIC, because this is what they did when they were young. Nowadays, they're not forced to move to some more modern programming languages, so they don't do. So here again we are. Why is security still separated from maintainability, functionality, usability, and availability? Why do we have a security conference? I've never seen an availability conference or functionality conference. This is something which comes automatically when you write your software. It has some functions, it has to fulfill some functions, it has to be usable, and then you think about maintainability. Nobody's caring about security, because security is just a cost factor. And I think this is utterly wrong. We need to change this. We need to talk to our kids. We need to talk to our youngsters. We need to talk to our education to get the security much, much earlier in. Usually what I say is, it's about swimming. Are you able to swim? Who's able to swim? Why? Because your parents taught you for your safety. Do you think of swimming, or do you think of safety when you're swimming? Of course you don't. We should teach the same thing in terms of security. I still have people who have to tell what a phishing email is. But they should do this automatically, with a change of mind. Someone's asking for your password, phishing, don't ignore and just delete it. But that's something you have to teach people. So to wrap up, I don't need any more standards. If you're working on a standard body on security, there are standards in the gas companies, there are standards in the petroleum companies, in chemical area, there are standards in the oil company in Europe, in the oil companies in Germany, there are oil companies in the US, 3 different standards. Electricity, there are lots and lots of standards of electricity in the US, in Germany, in the Netherlands, in Sweden, in Norwegian. And do you think they are all translations of the same standard? No, they are not. They are all adapted to the country. I wonder why. Too many standards. Please stop that one. We're talking about defense in depth. Of course we're doing defense in depth. Yes, we do network segregation. We do detection mechanisms. We're doing prompt patching where we can, even on oscilloscopes. Yes, we're patching our oscilloscopes, and we patch them promptly. And so far, I haven't bricked one. Still waiting for that day. Maybe I resign before. But still, our foundations are flawed. I buy devices which cannot be secured. I buy devices which are not robust. And I think this is something we have to change. We need to have an agile vulnerability mitigation life cycle. I would like to be able to patch any device I have as quickly as possible. Or do you think you will have a Patch Tuesday for your house? Think of a Patch Tuesday. Nowadays, Patch Tuesday is easy. It's automatic on my Windows PC here. Maybe I'm one of the few who is running Windows here. But later, Patch Tuesday, I have to go around in my house, update the Wii, update my Apple TV, update my smart meter, go out for the car, then the fridge, my nice espresso machine. So I'm busy the whole Tuesday afternoon patching my device. You know how often I am pissed off of my Apple TV? Every time I'm using my Apple TV, very rarely. Every time I'm using it, it's saying, there's a new download for you available. Do you want to install it now? No, I don't want to. I would like to have it happen in the background, but it's not. So do you want to do this? No, I think we need to be much more agile. I would like to see something which is more robust so we can apply the patches automatically. I don't want to run around every Wednesday and every Tuesday a month and patching all my devices. And the devices are not getting fewer, the devices are getting more. Certification of end devices. This is what I'm looking for. The recipe of some real security experts who can tell me you run those 3 tools, those 10 tools, in the default configuration. They're all open source tools. You just download them. You shoot them at your device. And if it's all showing green, then your device is reasonably secure. I'm not saying I'm asking for in-depth security, but we're talking about robustness, resilience, something at the basic level. And as long as my devices are failing Nessus, I don't need to have penetration testing. Once Nessus is fine and all the other test suites are fine, then we can look at penetration testing and go deeper. But as long as my devices still fail, I don't need to have more. But someone needs to come up with this list. I can't do this, but maybe some of you guys can do this. Come up with a list of testing and saying, okay, you run those tests here, shoot this against the device, and if everything is fine, you can claim that this device is resilient enough that it can be put out into the field. IT technology is not bad. Still, there are lots and lots of control systems which believe they have to reinvent the wheel. And I think this is something we have to also change. At least with us, our development now is using the same technologies we're using for the computer center. Maintaining a computer center, we're using Puppet, Git, Foreman, some other tools. We're doing the same tools we're now using for our control systems. Software development, Atlassian, Jira, again Git. We're using the same tools now for our control systems, having nightly builds of our software, making regression tests, looking what were the changes. Do the changes have some impact on safety, safety applications? We can run security scanners in parallel, static code analysis on our software to figure out, is the control software reasonably secure, at least to the standard of our secure static code analyzers, and so on. But this is something where we needed to make a step forward that our developers are accepting this. And we don't have few developers. We're talking about something like 300 to 400 developers just doing development of control systems. And last but not least, swimming in security. I think we have to go back to our universities and see whether the teaching of security is well and nicely embedded into the overall curriculum. Is this done at the right time? Is this done too early, too late? Do we want to have security courses at all, or do we want to have the security courses embedded with each of the different topics? I don't know, but I think this is open for the discussion. So if you want to see more about CERN, there's a film called Angels and Demons. 5 minutes are donated to us. If you're younger, there's also a film of Muppets. You're happily invited to come to CERN. We have public tours. Not anymore underground because we are now shutting down the accelerator to restart it, but there are lots of other itineraries which you can have a look at. If you want to see our computer center, just go on Google Maps, draw the small minifig on Google Maps onto the computer center, and you can move around our computer center to have a look inside. For those ones who want to be challenged, we have hidden something like 30 small Lego minifigs in the computer center. If you find them all, you get a small gift from me, maybe a T-shirt with a Lagrangian like that one. Thank you very much. Questions? Oh? Yeah. Let them leave first. So. I shouldn't have said thank you very much. No, we're taking public questions. Go ahead. So the question is, what do I think about nuclear reactors and the security or the cybersecurity nuclear reactors? This what is your question? Legacy device. So I'm not coming out of the field. What I know, at least from the energy companies which are running nuclear devices, the IAEA in Vienna and so on, I think they're doing a vast effort in securing their devices and having the same safety levels in cybersecurity than they have in normal safety. So I think they're doing good, but I'm not an expert in giving you the right answer to that part. More questions? Oh, yeah.
Maybe not a question, but a comment that from vendors, what we hear that they want requirements from the end user. Like you say, like you give me device, and the vendor says, like you as the user give me the requirements. What do you want to have in a device? The other complaint is that yes, we already start implementing a lot, but the problem is that they take devices, they do nothing. They switch it off, or they do not apply it in the right way, and you cannot control it. So this is like kind of mutual, you know.
I get your point. So the point she's making is that lots of vendors are asking for input, how to secure the devices. And I think we're a little bit more generalizing here. There are vendors which are very, very proactive, and they're doing very good in protecting the devices and trying to talk to the community. There are other vendors who are completely ignorant. So the truth is somewhere in between. Yes, you're completely right.
It's like you missed this point from your presentation.
I'm sorry.
On your calculations, how much damage do you do whenever you have to remove from patching? And from a wrongful patching, what would be the outcome on the wrong results? Let's say you patch the device as your vendor told you to, but then it so happens that the device wouldn't boot again, and you have now that box. You got a brick box.
For our control systems, in principle, we've made an assessment. Each control system has made its assessment. Their control systems. Second? The question is, what is the consequence when we're doing the patching? Is there any risk to the patching? So we've done an analysis. There are some systems, like the drill machines or the laser cutters, where I don't care. So there you can patch any time. The worst thing which can happen is that the laser cutter's down for 48 hours because I have to get somebody from the support in, from the home country to make the repair. We don't care. For the systems which are sensitive, which you cannot reboot at random times, we slot them in during the maintenance windows, which is every 6 weeks, and then we do the patching every 6 weeks. Or even longer. We get some systems which haven't been patched for a year, because those systems need to be up all time, and then we have fenced the systems and put all the bells and whistles around to make sure that if something is happening, we get early warning. In any case, for all the control systems we have, at least what we can say is, if the servers are going down, the Windows PCs are going down, we bring the machine, we bring the beam into a safe state, which means that if you think of this 80 kilograms of TNT, there are exit methods to exit this 80 kilograms of TNT. And once one system is down, the 80 kilograms of TNT is more or less exited, and then it's in a safe state.
You talked a lot about control system vulnerability. In your experience, have you also seen an increase in control system threats? So this is the possibility, but have you seen in the last 5 years, 10 years, 1 year, an increase in active real-world threats?
I don't have the statistic on this. So I've shown some of the media articles I'm reading. You have to fold out now that media is giving more attention to those vulnerabilities and those attacks, so there might be an increase automatically because of media coverage. I can't verify whether everything what has been written there is true or not. I have my doubts. Concerning CERN, at the moment we don't see any big change in the threat scenario to CERN. So we have, for example, so far not seen any dedicated attack against the LHC. Or we're not aware of that. More questions?
From that whole question, what happens when a device is, let's say, infected by a malware and it starts attacking the rest, and it's a sensitive device? What happens then? What's your best practice?
So in that this would be something like a bad case scenario. Yeah. If a device infected, starting infecting other devices, in principle.
Let's say just that device specifically is one of those that they have thrown all year long, and you didn't have any chances to turn it off.
Oh.
But you know that it's infected.
No, the chance to turn off, we get always the chance to turn off. So in the worst case, we turn off, but then we lose beam time, which means that we cannot run accelerators. In the end, the costs are controllable. So then in that case, we would just shut down, reinstall, or make sanitization, then we clean. But we had cases where, on the other side, for the experiments, you know the digital cameras, we had once an experiment in 2007 which was compromised. And that system we did not shut down because if you look at CERN, if you're a small experiment with something like 50 people, you build up your experiment, you get in the beam, you get 2 weeks of beam time, which means you get a 2-week slot where you can get collisions. And unfortunately, what happened in that case was the device was compromised 3 days within this 2 weeks of beam time. Shutting it down at that very moment would have meant that the experiment is done for the year, no data. So you can't do this. So what we were doing in that case, we did 3 hours forensic and looking what happened. Then we fenced the server, and we had a completely compromised server running for another 2 weeks at CERN to let them finish the data taking. Afterwards, we shut it down. So it's a triage. You have to see, but everybody is doing this. If your computer center is compromised, I think nobody is shutting down the computer center when it's from compromise. First, you try to figure out how it happened, what happened, and whether it's worth it shutting down or maybe we can mitigate it differently. More questions?
The threat profile of the control system environments is somewhat unclear. How do you justify the costs of installing so many security updates and built-in security plans?
So the question is, without a concrete threat scenario, how can you justify costs? I can't. So in principle, but why should I justify costs for security? I'm not justifying costs for functionality or usability or maintainability. I'm not justifying costs for availability. So in that case, security is, again, it's one of the IT things. It's ending with ITY, so it should be treated like the other ones. In principle, we got a risk assessment, so we know where we have to concentrate, because I cannot invest in any corner to do security better. So we know more or less from assessments where we need to invest more and where we can be a little bit of, say a little sluggish and not do anything.
I have a question regarding change control and the control systems that serve. Is there a QA path environment versus a production environment, or are all strictly?
You like poking into my wounds, aren't you? The question is, do we have a QA environment for our control systems? The LHC is a prototype. There's only one LHC in the world, and no, for that one, we don't have a second one. So most of the control systems have test corners, test stands, where you do the software development on in the first iterations. But at a certain level, you need to move to the real device, because the interaction between accelerators and the control system, the controls loop, are quite complex, and this is where you can only do it with having the real machine live, sometimes even with having beam in the machine. But this is then where restricted development can be done. So we get a balance on this one. It's not the most optimal balance. We're trying to move this more to the test stands and far away from the accelerator. But at the moment, yes, we get a QA to a certain extent, and then we need to go live. It's a little bit different than in normal production plants, where they have a full-blown test stand for everything, and then they can roll out into the plant. We can't.
Just a further question. If you're able to do that at a subsystem level, it sounds like, is that 50% of the total system?
Depends on the system. Some systems are very, very independent of beam. and independent of the machine, there you can do all the testing. For example, if you look at industrial controls, cryogenics, cooling, ventilation, electricity, those devices are standard industrial installations which you find everywhere else. They are developed completely offline on test stands, and then they're rolled out into the field. If you come closer to operations of Xcelerator, the more you come to dedicated hardware, dedicated software, and this is where your shift is then going more towards the Xcelerator. But there's still some area where we can work on, and we do work on. More questions? Yeah.
You mentioned that you're not looking for any more standards. What are you looking for from governments?
From governments? I think I will not delve into this question. I will not answer this question. At the moment, the government's investing lots and lots of money into security, but I don't see whether this money is really giving products which are useful for, at least for us. So, but no more standards, please. Just, yeah. So do we have control systems where we decided due to cost reason not to patch them? In principle, not patching because of cost or not patching of not be able to are two things. If you can patch, there's a paradigm which means you must patch. At a certain moment you need to patch. Usually we're following standard evolution, so moving from XP to 7, moving from Red Hat 6 to Red Hat 7 or Red Hat 5 to 6. This is the breakpoints where we have to upgrade in any case. So we have a very few systems which are not patched, but all those systems are like the CAD/CAM systems, which are in principle, I don't care. Yeah, if this CAD/CAM system I've shown there, or the laser cutter, if they're getting infected, so what? They're getting infected. They are not sitting on our controls network. They're actually sitting even on our office networks. So they're sitting somewhere where they don't harm. And on the office network, if they're getting infected, you just reinstall and you start from scratch. The critical ones for operations we try to patch as soon as we can. But timely is always then, it's a definition. How do we do assessment of the systems? Oh, I think this is why we do this. In principle, every device we're getting in, we're trying to penetration test. So this is the first thing, try to get an idea how secure, how the device is set up. And then key for my work is inventories. Every device connected to our networks is registered in the database. So I know every device in our network. I know every account, I know every web page. We're now working on dependencies. So if your control system engineers are supposed to understand the dependency of a control system on other control systems, but also on the underlying technologies. So if you control system, you need to have NTP, you need to have a SHCP, maybe you need to have a file server somewhere, local database, LDAP, Active Directory, maybe you're based on Kerberos, maybe you need to have a single sign and so on. So this is all things which we are now building up in an No. I think I benefit just on the other side. Think of, in the past, there was a network team doing control system networks, and there was a network team doing IT networks. Now we have one team who's doing all networking at CERN. So we're taking full competence of them to deal with network connectivity at CERN for control systems and for the computer center. In the past, there were always a discussion about availability and reaction time, bandwidth, and throughput, and so on. But now it's the same. The same for databases. We don't have any databases anymore for the control sector. The databases at CERN provided by the IT department with database administrators who know what they're doing. So they're doing the patching of the databases in sync with the control system experts. So not necessarily very quickly, but quickly enough that it fulfills my needs, and we can operate accelerators. Operating system. For the control system, operating system are now coming from the IT department. So this is where the IT department is jumping in. We try to move everything away from the control systems, which are not genuine control systems. Operating system, it's IT. Web service, IT. Mailing, IT. Networking, IT. Wireless communication, IT. And so on. This is all now moved to it, trying to move it more and more into the IT department. Jira, Git, all the tools. At the moment, the controls people are running their own Jira and Git instances. But I hope that in the future, we can also provide this. Virtualization, this was a recent step we've done. Lots of controls development is done on virtualized hardware, and the virtualization cluster is maintained by the IT department. But this happened 10 years ago. When the control, if you look at the control system itself, the time when the vendors moved to the Windows platform and using TCP/IP instead of Modbus or Profibus or whatever else, this was the time where the threats and vulnerabilities creeped in. So I think you will never make the step back. You will never fix this again and move back to Profibus. I think the IT technologies have also the benefits. So I think we just have to get the security now properly integrated. And this is the big step. I'm completely convinced of this. Security team. My security team, we're dealing with all types of security incidents at CERN. Control system is just a part of this. But again, you've got a computer center. Is the control system failing or the main CERN homepage web server failing? What is more detrimental to the organization? Now you do a risk assessment, you can do some balancing and so on, you can figure out. But in the end, it's more or less the same thing.
You mentioned that you have programmers who've been working in Fortran and BASIC, archaic languages. How have you brought security development lifecycle into those groups?
So those groups are physicists. They can do the analysis. This is the freedom of academia which you have at CERN. So, control systems are not written in Pascal, Fortran, or BASIC. There we're talking about the analysis jobs to take the collision pictures and then doing the analysis on top of this. This is their freedom. They can use the language, and honestly, this software is not even security critical because what will fail is the analysis, and then they will get something which they don't want to get. So this is not critical. For the big projects, the control systems, there are environments where the people are all forced to program in C, C++, or in Java, and then you can have the software development lifecycle on top of this.
But I'm guessing that you do have archaic systems in your control systems.
Say again, we got?
You may have archaic systems, archaic control systems, so they're homegrown control systems or control systems that, are based on, somebody who developed something years ago and probably no longer with CERN, anything like that?
Do we have control systems which are orphaned? This is what you're asking. We're doing again and again life cycles on our devices. We're now running another life cycle. Every device, as I said, is registered. We're reviewing regularly whether devices still have an owner who is actually at CERN, who is taking responsibility.
And you have a life cycle process.
I'm very based on life cycles. For everything I can see, I would like to have a life cycle. Devices we're working on for web pages. You leave CERN, your web pages are either given to your supervisor or deleted. You leave CERN, your account is getting blocked, your mails are deleted, and your data is gone after a certain time period. You leave CERN, your devices need to be propagated to your supervisor, and so on. Firewall openings, I get a life cycle for firewall openings. You ask for a firewall opening, we do some initial testing, you get your opening, and every month we're looking whether there's traffic to your device and whether you still have an HTTP server, whatever you asked for, whether there's a service listening on the port. If not, we close this. I think inventories and life cycles are the most important things for me running security operations. And we,
But sometimes those things are mission critical, right? So then you have to, there's no option to turn it off. You have to transfer it to somebody else and they have to.
you have to find somebody taking responsibility. So this is the concept which I didn't introduce here, but I am not the person responsible for security at CERN. We have delegated security to everybody who is running systems. So if you are a control system expert, you are in first instance responsible for the security of your control system. And we are here as a security team, as your facilitator and your enabler, to get the security right with the IT department who's giving you all the tools. So if you're running a database, give the database to the IT department. You don't need to take care about Oracle and patching or whatever else. For orphan systems, we try to identify them as quickly as possible and then assign them to somebody who can take responsibility, or we kill the systems. Yeah. 5 more minutes.
So assuming that the level of effort that goes into doing the minimal security testing that you talked about, assuming that that's non-trivial, if you took that cost and put it on product A and set it next to product B that doesn't have that cost, how successful do you think you would be in convincing management that you need to spend the extra money on product A?
So how do you motivate management to invest into security? I think the best incentive for management in security is, from time to time, a small security incident. This is what's the most brilliant thing. Yeah, something like Heartbleed, brilliant. I loved Heartbleed. I'm sorry, I shouldn't say this, and you guys shouldn't write that. But why did I love Heartbleed? A, it was quickly publicized. It has sufficient impact in the media so that my management learned about this, and many other people at CERN learned about this. It was very easy to patch and fix, apart from some devices where we're still waiting for the patches from the big vendors, but most of the things we fix quickly. And I used this to change all the passwords at CERN, because I wasn't 100% sure that we didn't leak anything. I'm pretty sure that by 99% we didn't leak anything, but still, changing all passwords is also then in fostering the awareness of management. So this is what's working fine. Comparison between tool A and tool B, the priorities is operations at CERN. So first priority is safe operation, not harming anybody, not harming the environment, and not destroying the X-rater. The second thing is operation itself, and then comes security. Guess one more question?
Are you doing outreach with some of these smaller vendors to cajole them or convince them that they need to build security in?
Every time we find something, we talk to the vendors. We try to explain them why we think it's suboptimal how they've implemented this.
Are there any formal mechanisms? Do you have an industry group or do you work
Nope.
with other labs?
We had some information exchange between governments, which is called the Euroscasi, European SCADA Control System Information Exchange, where no vendors, but big utilities and governments were present. But we have never vendors on that body. So we're talking directly with vendors.
What is the response rate? When you talk to one of those vendors and you found something with the products, what's the response rate that they're actually going to fix it?
Big vendors, very good ones. So big vendors nowadays, they have certs. So we talk to the certs, we get lines directly to the certs, and they say, oh, that's not good, we'll fix it, and they will notify you. So we can improve, I think they can improve on that, to have a better disclosure cycle. Smaller vendors, the problem is they don't even understand what you say, because they bought the TCP IP stack from somebody, and then they're just using this TCP IP stack. And if you tell them that there's a buffer overflow, they just say, yeah, but it's a library from outside, so we can't do anything. So there it's a little more difficult. And again, then it depends on how critical is the application. If you look at the dosimeter reader, if you can have the password or not, this is not leaking any sensitive information. There's no data leakage, so it's not critical. So there we informed them, we said fix it, and I think 2 years later they came up with something which was more robust. You have to leave? Yeah, if you want to continue discussion, we can go outside.